Okay, welcome to lecture 2.7. Okay, here I'm going to do an example. I'm going to use our toy example, that formateur problem, where we have three data points, and I'm going to run a likelihood ratio test. Okay, so first of all, recall that for our case, lambda hat was 0.667. Okay, that maximized likelihood function. Okay, now when you do a likelihood ratio test, you need to have a restricted case, and so in this we're going to have our null hypothesis, call it theta 0, that equaled 0.15. Okay, when we do that, the value of our test statistic just equaled negative 2 times log of lambda, and negative 2 times log lambda just equaled L hat R divided by L hat U. And so if we take the log of the ratio, so if that's log of A divided by B, it's log of A minus log of B. That's one of the log rules. Hopefully you remember from something like freshman calculus. So our test statistic is going to equal negative 2 times log of L hat R minus log L hat U. Okay. Let's compute those things right now. Okay. Log of L hat restricted is going to equal, okay, so we go to our spreadsheet. The restricted case would just be where theta equaled 0.15. Let's see what we get. We get negative 3.957. So this is negative 3.957. So negative 2 times. Okay, and now the unrestricted case was when we just plug in theta hat, so the maximum likelihood estimate of theta, and that was 0.66667, and we get negative 1.909. So minus negative 1.909, and hope you'll trust me. Do the arithmetic on that. You get 4.09. Okay. Now, let's see. Let's do a statistical test. Okay. Now, you have on Dropbox, it's something like 02.chi-square-table.pdf, and it's just a copy of this page. Okay, now I want you to see on that page, the very left, it says degrees of freedom, and then below that it says 1, 2, 3, so on. Okay, usually you're just going to look at the case for where the degrees of freedom equals 1, and then it has various p-values. Okay, so this may be hard to read. You should have the sheet, and tell you what I'm going to do is I am going to rewrite these numbers. So for different values of p, the chi-square table, where the degrees of freedom is 1, we have for 0.95, the number is 00. The critical number is 0.00393. For 0.5, it equals 0.455, and for 0.05, the number is 3.841. Let me give you a hint. I actually picked that when I picked a null, 0.15, I picked a number so that we would just barely reject. So our number is going to be 0.409. I wanted it to be just a little bit higher than that. That's a hint where we're going. Okay. Before I explain that, though, let me show you what a chi-square distribution looks like. Okay, so recall that, so chi-square with 1 degree of freedom, it equals a normal random variable squared. Okay, so if we have a normal distribution, say centered around 0, okay, we just take the square of that. And what that looks like, once you take the square of that random variable, it's going to look something like this. First off, it's squared, so it can't, the value cannot be less than 0. Okay, so it's going to look something like this. It's 0 here, and then it has an infinite tail. So because the normal has infinite tails either way, you square them. If the normal random variable is in either tail, it's going to appear in the right tail in this chi-square distribution. Okay. And then what we have, so these values, so if the critical value is 0.00393, we look that up on a chi-square distribution. What it means is 5% of the area is going to be, or 95% of the area is going to be to the right of that number. Okay, 0.455. That means 50% of the area is going to be to the right of that number. And then 3.841. Okay, so that means 5% is going to be to the right of that number. Okay. So, and then our critical value was 4.09. So when we reject, and we call this a one-tailed test, but in a way that's not quite right. It almost doesn't make sense. It rarely makes sense to do a two-tailed test for a chi-square distribution. So you would, if it's a two-tailed test, it would mean we would reject if it's in this region or if it's in this region. To reject on this side, it's kind of strange. The only way we would get a value below that 0.00393 is if our theta hat equaled something very, very, very close to 0.15. So if we got something like 0.15001, we'd be in this tail. And you think, like, wait, when would you ever have a test where you reject if it's very, very close to your null? Okay, it almost never makes sense to do that. An aside, bit of trivia. Here's the one case I've heard of where it might make sense to do that. It involves Gregor Mendel, the monk who did the early genetics research. You might remember from high school biology, the peas test, and something about Mendel grew these peas, and because of if it was recessive, then you'd get the small plant. But if it was at least one of the dominant, I can't remember exactly. But what he got is he reported his results, and the theory said that he should get something like 1/4 of them equal to these short plants. And it turns out he got like almost exactly that number. The null predicted 0.25, and the value he actually got it was 0.25001, something like that. And there's some historians who think that he fudged his results. He probably threw out some of his outlier observations. Sometimes this happens, but they were too fine-tuned. They were just too close to being just right. Okay, and in this case, Mendel's results. So he had results that were too close to being perfect. And if you're one of these historians, wanted to say, did Mendel fudge his results? You would look in this case. Okay, are his results in this left tail? That's one of the only cases I've heard of where you would look for something like that. look, usually what we're going to do is look for cases where it differs very much away from our null hypothesis. And for our toy example, this is what happened. Um, okay, so in this case, here we would reject. Okay, now what do I want to do? How long? You know what? I think I'm going to end there. Okay, so here's an example of running the likelihood ratio test and got that we could reject. Okay, see you in, God, I can't remember. I think it's 2.7. Okay.